This is Jahidul Islam. Now I want to represent my second homework and chapter 2, Indium Gallium Phosphate, Gallium Arsenide, Heterojunction Bipolar Transistor Foundry, and it's chapter 2 from the book of Introduction to MMIC Technology book. The topic Introduction to Foundry Service, and here the block diagram of the foundry service process. And there are four main sections: customer, circuit simulation, circuit layout, circuit evaluation. And customer requested initially the company, then the company have a design rules library, and there is a very important some specific section: design rules check, mask making process, recipe generations, front side process, back side process. Finally, after packaging, it is very important to evaluate by customer, and also self evaluation is important. Now I'll discuss introduction to indium gallium phosphide, gallium arsenide, heterojunction bipolar transistor, very basic process. And the first is the figure. This is the figure of heterojunction bipolar transistor basic structure, and it is the structures or schematic of the front side 6-inch heterojunction bipolar transistor process, and it is the front side flowchart, and beside is the back side flowchart. The front side flowchart have 21 section. First is the emitter contact, and the last is the passivations. Back side of the flowchart there are very less sections, but all are have several subsection. Types of the process and their merits. Three types of process are detailed in table. And the first is the process is the high power HP process, and practical applications PA of GSM and TCS and base stations, and it's several characteristics and breakdown voltage 20 to 23 around voltage, and it has frequency maximum DC gain 8 to 7. Another two process is high linearity ASL process and high speed AES process. Active devices and active devices, we know that indium gallium phosphide, gallium arsenide, heterojunction bipolar transistor is an active device, and it is actually a transistor, but it is a heterojunction, not homojunction, and the active device must have the characteristics of amplification and the non-linearity. Additionally, it requires a DC bias. In this section, only heterojunction bipolar transistor are mentioned. We can see in the slide the figure cross-sectional view of the indium gallium phosphide or gallium arsenide heterojunction bipolar transistor. And first section substage, semi-insulating substage, then the sub-collector and collector base emitter. There are several contact, emitter contact, and at the top and right side and left side there is a base and collector contact. Active devices, we know the heterojunction bipolar transistor is an active device. The high linearity ASL process, its active device is so named because of the intrinsic device linearity of the indium gallium phosphide HBT, which is the result of uniform current gain characteristics. In turn, the gain characteristics are a function of the collector current, the independent collector capacitance, and the high early voltage. We can see two figure, and figure this figure is the micrograph of the indium gallium phosphide gallium arsenide HBT. FECM image is a basic structures that layer by layer. In the figure, the indium gallium phosphide layers is shown. The purpose of the indium gallium phosphide lathes is to prevent surface recombination currents. The lathes performs a significant role in the reduction of 1 by F noise. The reduction of 1 by F noise concerning the emitter base spacing arises because of the reduced recombination current. And we can see from the figure the indium gallium phosphide lays between the emitter and base. Modeling. In this section, an extractions of the parameters of the BBIC model is presented. The parasitic, intrinsic, DC and IC parameters are required to achieve a perfect model. The modeling device reported here is based on the 6-inch indium gallium phosphide gallium arsenide HBT device technology, which utilizes one emitter finger with a width of 3 micrometer and an emitter length of 20 micrometer. It is one kind of modeling measurement setup. This picture picked up from the Kangon University, and here is the measurement software, here is the prop station. The heterojunction bipolar transistor device characteristics, very important characteristics. It has that are represented in the table. The parameter beta, the gain is a very important parameter. HBT device again approximately 112, and FT another characteristics, gigahertz in range and 50 gigahertz, F max 85, and breakdown voltage BCEO 12 volt, and breakdown voltage BCBO base terminal at 23, and V turn on voltage 1.20, B offset voltage 0.1, and the efficiency 1.02. These are very important parameters or characteristics of heterojunction bipolar transistor. And we know the BBIC model from the first chapter. The BBIC model was developed as an industry standard replacement for the SGP model. Additionally, the BBIC model was intended to improve the deficiencies in the SGP model that have become apparent over time because of the advance in BGT process technology. Unlike the conventional SGP model, which has 3 terminals, the BBIC is a 4-terminal model and comprised of a base, an emitter, a collector, and a substrate, which are denoted by the letters BEC and ACE. It is the equivalent circuit of BBIC model. The extraction of the parasitic elements and parasitic elements. Firstly, we will discuss the parasitic capacitance. Parasitic capacitance or stay capacitance is the unavoidable and usually unwanted capacitance that exists between the parts of an electronic component or circuit simply because of their proximity to each other. As observed, the parasitic capacitance in the input and output to the ground are CP1 and CP2. That means the input here and here ground, between this terminal and ground, this is CP1 is the parasitic capacitance CP1, it is the parasitic capacitance CP2, and it's the equivalent circuit. If I can draw the equivalent circuit from here, this is this equivalent circuit, and it is the photograph an open pattern for in the to understand the parasitic capacitance. This is the figure, and I collect from the book the parasitic capacitance relations with the frequency. We know the capacitive reactance in ohms is equal 1 by 2 FC, 2 pi FC. Here, from this relation, we can understand the frequency is inversely proportional with the capacitance. The another parasitic elements is the parasitic inductance. The parasitic inductance is an unwanted inductance effect that is unavoidably present in all real electronic devices. The parasitic inductances are exerted by the short patterns. The Le and Lb and Lc indicate the parasitic inductance. E denote the emitter. The inductance, parasitic inductance exerted from the emitter is called Le. Such a way we can denote Lb and Lc. It is the photograph of short pattern, and this is the relation of frequency and the imaginary of jet uh, parameters. These parameters we can calculate it from different equations that are incorporated in the book I collected from the figure from the Introduction to MMIC Technology book. Overlap capacitance. The overlap capacitance is a parasitic capacitance that arises due to the geometric overlapping between the base and the collector in the HBT can give the rise to charge feed through. There might be a small area where the base region physically overlaps the collector region. That means it is a capacitance that actually geometric overlapping capacitance, and it occurs in very small area. From the figure, the fitting of the sum CBC plus CBCO function for junction capacitance. Here CBCO is the overlap capacitance. Then I will discuss the embedding. Embedding is the process used to remove the influence of unwanted electrical elements, typically the parasitic components and parasitic capacitance, parasitic inductance, and overlap capacitance introduced by test figures from the measured electrical response of a device like HBT under test. Heterojunction bipolar transistor, HBT, we know already. And from the figure, we can understand easily. That is, from the figure B and figure C, you can understand here the parasitic elements are eliminated. And these three steps represent the de-embedding the procedure. Then the resistance. It is one kind of impedance. The base collector and base emitter junction capacitance increase with zero voltage and high current, ignoring the base collector and base emitter impedance. The resistance value is determined by the average resistance in the flat frequency region, ignoring impedance. This is the graph for resistance versus frequency. Is the equations we can find the others equations, and finally, and is the RE and is the RB is the RC. Consequently, the values of RE, RB, and RC are 1.43 ohm, 1.17 ohm, and 1.41 ohm respectively. It is the IV characteristics curve. Uh, it is the IV characteristics curve of HBT. The IV characteristics curve under the constant voltage, and here the voltage is constant, and but this IV characteristics curve, the current is constant. So that's why there is a difference between the curve pattern, and all two figures are simulated figure. Junction capacitance is another important factor for HBT transistor, and the junction capacitance is the depletion capacitance that forms in a junction under zero bias. That means it occurs at zero bias. We can understand from the figure. The figure of junction capacitance versus base emitter voltage. It is the CB. That means base emitter capacitance curve. It is the base collector capacitance curve. From these two capacitance, we can find out under zero bias the junction capacitance. Passive device and transmission line. A transmission line is a specialized cable or other structure designed to conduct the electromagnetic waves with minimum losses and distortion. The physical parameters of the line metal are shown in figure. This is the figure. Here we can denote different physical parameters, but this is not a clear. The additional physical parameters we can understand from the table clearly. The silicon nitride dielectric constant, its value in case of the HBT 6.8. The gallium arsenide dielectric constant, its value 12.85. Silicon nitride dielectric loss tangent, its value 0.002. The gallium arsenide dielectric loss tangent, its value 0.006. The gold plate ABM thickness 4 micrometer, standard deviation 10%. Silicon nitride position thickness 1000 Armstrong, Cg 600 p Faraday per millimeter square. The gold plate IM plus IMS thickness 1.5 micrometer, standard deviation 10%. The gallium arsenide substrate thickness 95 micrometer, standard deviation 10%. Now I will discuss passive devices, some passive devices. Firstly, I want to tell about beam capacitor. The metal insulator metal capacitors are another class of compact capacitors with distinct advantages. They are like a parallel plate capacitor in which a metal plate electrodes are separated by a insulating material. This insulating material is called dielectric material, and the reference plane of an MEM capacitor device. Here we can understand the two port, one port, two port, and between them there is an insulating material that is called dielectric material. The spiral inductor is one kind of multi-turn planar inductor with multiple dielectric layers. We can easily differentiate between the spiral inductor and the previous dielectric uh, dual inductor because there is a multiple dielectric layers. We can understand easily from the reference plane of spiral inductor. A turn in the spiral inductor is the length of a complete 360-degree revolution. The width and spacing of the strips in the spiral inductor are uniform throughout. Then now I will discuss the resistor. The resistors in an MMIC can use the topped semiconductor layer of a deposited thin film resistive layer. In this case, the material of the resistor is a nickel chromium thin film. Here, the sputtered thin film resistors offer improved linearity and lower temperature coefficient in comparison to that of others. And this is the configuration of resistor, and this is the effective length where we can feel the impedance, that means resistance. Now I will discuss the design rule type. Here we can see a layout for design rules, and the first, the width and length, spacing of layer 1 to layer 2, extension of layer 2 to layer 1, overlapping of layer 1 and layer 2, surrounding of layer 1 by layer 2. These are the illustration of the layout design rules. 6 types of simple layout design rules are described in the table. And these 6 types are very important terms. The terms, first one, width. The definition, the shorter dimension of all objects in any direction on the named layer. Then the length, the longer dimension perpendicular to the width on the named layer. Then spacing, the distances that separating all pairs of objects either on the same layer or between two different layers. Number 4, extension, the amount that an object on one layer must extend beyond the ends of an object on another layer. Number 5, the overlapping, the amount that an object on one layer must overlap an object on another layer. 6, the surrounding, the degree to which an object on one layer must be completely surrounded by objects on another layer. Different layer descriptions. There are 19 layers used in the fabrication process of Keiko. Different layer ID, different layer name, 19. And sequentially, emitter contact first, last is backside scribe street. And there are 2 types of photoresist, either positive or negative, and the area can be clear or dark. Now, concrete layout design rules. Now we will know some design rules important. The following design rules are specifications for the wafer as given by Keiko. 1. Topic 1. Nickel chromium resistor. Nickel chromium resistor is the layout design rule for the nickel chromium resistor, and different types of nickel chromium resistor type, and there are some specific rules on the basis of different type. Minimum width of NCR in case of NCR01 2 micrometer, NCR02 5 micrometer, NCR03 2 micrometer spacing, NCR04 overlapping of NCR and IMS equal 2 micrometer, NCR05 minimum IMS or NCR perpendicular kind flow equal 0.2 micrometer. And another 2 is NCR06, NCR07. Then second, interconnect metal sheet. The IMS is a layer that is the pattern before sputtering the sheet metal for electroplating. And IMS 01 and minimum width of the IMS in the active device area equal 1 micrometer. We can understand easily the use of IMS and IM. Here 1 IM SO4 minimum surrounding of FNB by IMS equal 0.2 micrometer. Number 3, for concrete layout design rules, interconnected metal, that means interconnect metal IM. The IM is the first layer of metal fabricated by electroplating. Is the IM01 is very important. Minimum spacing between IM and IM equal 2.4 micrometer. IM02 fixed surrounding of the IMS by IM equal 0.3 micrometer. IM03 maximum current density of the interconnect metal equal 10 milliampere per micrometer. IM04 no donut pattern allow. The second, nitride via S and V, and it is the regions that we can denote S and V. And SNV01 minimum width of the SNV equal 3 micrometer, SNV02 minimum surrounding of the SNV by IM equal 1 micrometer. Transmission line, The transmission line is composed of two layers, IMS and IM is the transmission line 0.3 micrometer. Here is this range is the transmission line. 6. Air bridge post ABP and ABP design rule layout is the layout of ABP design. ABP01 minimum width of the ABP equal 4 micrometer. ABP02 minimum spacing between ABP and ABP equal 5 micrometer. ABP03 minimum spacing between ABP and IE equal 5 micrometer. Finally, ABP05 minimum sounding the S&P by ABP equal 0.5 micrometer. Then I will discuss another section of rule, air bridge metal ABM. ABM, this is the layout of ABM, and here we can discuss ABM01. Minimum width of the ABM equal 5 micrometer. ABM02 minimum spacing of ABM to ABM equal 5 micrometer. ABM03 fixed surrounding of the ABP by ABM equal 0.5 micrometer, and ABM04 ABP must be corners of the ABM. The ABM05 represent here maximum current density of the air bridge metal equal 20 milliampere per micrometer. ABM06 is denote the no donut pattern allow. Now I will discuss the final passivation layer FPL is the layout of this ABM not is also include FPL. FPL01 the minimum width of the FPL equal 30 micrometer. Here ABM not correct, here will be FPL. So FPL02 the minimum sounding of the BSS by FPL equal 12.5 micrometer. FPL03 the minimum spacing between FPL and FPL equal 30 micrometer. Finally I will discuss the pad. This pad equal different structures included here, FPL, ABM, ABP, FNB, IMS, IM, SNP is the layout of the pad. The PAD01 first, and the minimum width of the bond pad is determined by the assembler's capability, and the typical bond pad size is 100 micrometer multiply 100 micrometer. The pad 02, the minimum width of the test pad equal 75 micrometer. Pad 03, the minimum spacing between two pads equal 25 micrometer. Pad 04, the minimum surrounding between bond pad and FPL equal 12.5 micrometer. PAD 05, the minimum spacing between the scribe line ends and the bond pad equal 12.5 micrometer. This is the last slide for me from my point of view, and DRC, design rule check. The DRC is an abbreviation for the term design rule check. That is, the engineers need to check all or part of the design to confirm whether it meets the manufacturing specifications. There are two types of DRC, and one is a quick check. The other is custom check, which is carried out according to a pre-written set of rules, and this DRC procedure is given below. Is the very simple schematic, and define or select a design rule, then run the design using defined or selected rule. In third section, load the result. Lastly, view any error that were found. Thank you all.